Hello, everybody. I will present the outreach of the AMADEE-18 Mars analog simulation. I will present first the architecture of the mission and then go through each experiment to try to explain you furthermore, and then go through the outcomes and lessons learned for the next mission. But let me introduce myself first. I'm Aline Decadi, so I'm an active member of the administrative committee of the French Mars Society. I'm an aerospace engineer passionate by Mars, and I'm part of the Australian Space Forum that has organized this Mars analog mission in the desert of Oman. So I will talk about this today. I had several roles during the simulation. So I was a spacesuit technician. I was also a safety officer. I did various experiments on the field, and I'm also an analog astronaut in training. The Australian Space Forum is a citizen science organization. So they have a patent on their own outdoor spacesuit simulator they are using on the field during the EVAs. They basically organize a mission which is really Mars analog dedicated every 2 years. For this year, they have worked in close collaboration with national and international research institutions, industry and politics. You can see here the signature of the Memorandum of Understanding between the director of the Australian Space Forum, the Omanian Astronomical Society, and the Sultanate of Oman. So Oman has been selected as the host country for conducting the analog mission this year. It took place in February. In particular, the region of Dhofar has a number of scientifically interesting sites, and also they have a high level of security and infrastructure. The mission has been called AMADEE-18. It has been a 4-week mission on the field, and we have simulated 20 experiments. Actually, 100 people were involved for working during the mission from the beginning. Actually, we spent 1 year to prepare this mission, elaborate the experiments, and also the operational procedures to be executed on the field. So the real aim was to have some outcomes that are useful for getting closer to Mars. Here is the mission architecture. So you see in blue the Mission Support Center, which is located in Innsbruck in the Australian Space Forum premises. During the simulation, we have introduced a time-minutes delay to account for the average signal travel time between Earth and Mars. And on the left, in red, so the Mars habitat. I will come back to it in a minute. Just to show you one picture of the Mission Support Center in Innsbruck. This is the centerpiece of the ground segment of the mission. They are interacted with numerous external organizations. And during the mission, and this is the single point of contact for the field crew. Here are the field crew members, the 15 field crew members. So we have several functions to be ensured during the mission: the field commander, the people in charge of the operations, the science officer, the safety officers, people in charge of the maintenance of the spacesuit, medical officers also, and people in charge of managing supplies and resources on the field. Of course, water, power, and the analog astronauts. So actually, these functions are interchangeable. So so we can shift the role one day to another. But during the training, we have been trained in order to be experts in one role and also in one or two experiments. This way we were the experts and be able also to debug all the hardware and software programs during the training period. This is our Mars habitat, so the space segment. So it had to be autonomous during the mission. So for this reason, we had on the right the kitchen, the dining area, the storage for the food, water containers, energy, and you can't see, but on the left, we had at some point some generators before the mission. On the back, we had the containers that were dedicated for the crew rest. So there were rooms with showers and lavatories. On the left, we had containers that were used for operations, science area, and the spacesuit themselves. And within the dome, at the center, we had different spots, a medical center, a sport area, a medical workshop with various tools, and experiments that need space in order to be operated and executed, like 3D printing technology, the rover, and the drone. So during the mission, the 20 experiments that we had executed were technical ones. So some of them requiring EVAs up to 15 kilometers from the base in the field of robotics, geoscience, navigation, and communication. We had also inside the base station some experiments dedicated to astrobiology, 3D printing technology, and maintenance of equipment devices and spacesuits. We have also performed human factors experiments that were completely included in our daily schedule in order to assess psychological effects and evaluate the fatigue, which can be physical or mental fatigue. So I will now go through each of them in order to give you more hints about what it is. I think I won't have time to go through a lot of human factors, but if you have any questions, then I will be happy to answer. Let's start with the Rover HUSKY. It has been developed by the University of Technology de Graz by the Dr. Gerald Steinbauer. It's an autonomous rover, so the aim is to do a 3D mapping of the terrain and classify it. So basically, whereas the analog astronauts arrive on the field, HUSKY has already started mapping it in 3D autonomously in order to identify potential hazards and assess if the localization chosen for the experiment is secure or not. So it means no hidden holes covered by a pile of sand, for example. I would like to show you how it worked. Okay, so it's the mapping of the base station. So you will recognize each part at some point. So you can see this is the laser scanner that are rotating 360 degrees and is mapping around. And as you can see, there's the dome that appears. And at the same time, it's classifying to say where are the potential problems and where we shouldn't go. So each time there's orange and red. You can't go there. And so at the front side, you can see the fences, so it was also something that it wouldn't go there. So the results. So he had almost fully autonomously mapping the base camp, and also he did the same on the field. So it was a viable basis for continuous cooperation and integration of robotics in this kind of mission. Nevertheless, we have, of course, lessons learned to be fixed and open point to be discussed and analyzed for further mission. So there are the autonomous concept of the rover itself. It's complex for implementation. It needs human support, so it's a question, do we really need this? The terrain, of course, locomotion, perception, and the stability of the rover in the sand and over the dunes, where it goes somewhere that can be hazardous. The environment itself, the variation of temperature and the sand, they are well known, but still to be taken into account. It can be, we had experienced some push button that was blocked, so not functioning anymore due to the sand. And also, we had some procedures for debugging the software of the rover during the mission. And for this, we have also identified open points that we can fix for the next mission. Be more situation awareness, if I can say. I would like to talk about the drone that is called AVI-NAV. So it has been developed by the University Alpen Adria by the professor Stefan Weiss. So actually, these experiments verify if an unmanned aerial vehicle is able to navigate autonomously, purely on visual inertial cues, and with an onboard processing over Mars-like surfaces. So I would like to show you a video also. By this time, I can explain you a little bit. So it's equipped with sensors, GPS, EMU, camera, a processing unit, an algorithm framework that allows the aerial vehicle navigate autonomously to predefined GPS waypoint. There's the onboard camera that record the imagery and synchronized the EMU and the GPS data for verification of the visual inertial odometry. This is done by post-processing. So in terms of results, we observe that there are some parameters that are very crucial for the mission success. This is the texture of the terrain and the time of the day. So the time of the day determines the casting of shadows on an homogeneous surface like sand. Shadows are the only source of texture. So we observe that the little rocks were enough to create this texture, so it was very, very good for us. In terms of lessons learned, we have seen that the flights in early mornings or late afternoon have been beneficial because of the larger sun inclination and subsequent shadows that aim to contrast the image. And also, we have tested it in lighter conditions, and we have also observed that the change of shadows have a negative effect on the performance of the visual inertial odometry. But that's normal. There's also a point that has been fixed during the mission itself, was the self-cast shadows on the ground. So they have required an outlayer rejection by post-processing. But yeah, as you have seen, he found a way to do the calibration process, and the data at the end have been post-processing without any problem. So that was a success for this run. We did also geo-sampling, so sampling of selected rocks, transmitted the description verbally to the operation center. And then we do some imagery thanks to the camera, which is located close to the helmet of the analog astronaut. So the picture is directly sent to the operational center by the telemetry. And then the samples are collected in small bags and stored in the box that is on the chest on the astronaut here. We have used the 2D printing technology to do the red tools that you see for collecting the samples. So this is the basic material used is a red filament that build the tools layer by layer. And this is done by adding manufacturing process. Here we did field spectrometry for determination of the mineralogy and geochemistry of the terrain. So it's an experiment from the Italian Space Agency. So here we are proceeding the acquisition of the reflectance and radiant spectra in an analog environment to Mars. On the right, you can see a subsurface scanning experiment. So actually, a ground-penetrating radar detects the variation of the dielectric properties of the ground while it is scanning the subsurface. So these two experiments are geological instrumentation. They are computerized and for direct compilation of the data and the exploitation of the field. You can see here the Water Explorer experiment on the left. So it's consisted in positioning geophone nodes by the analog astronaut. So the experiment is to record both active and passive seismic signal to delineate the shallow aquifers. Here you see the analog astronaut generating a source, active source, with a hammer and a metallical plate. And the one of the right is a radio navigation system for a GPS-less planet. So the aim is to measure the distance with the speed of radio waves. So basically, we needed 3 fixed ground stations used for the calibration of the relative values. And the analog astronauts were carrying a transceiver to be trackable. And so we have measured the needed time from one receiver to another one by calculating the distance and the location calibration of the stations. We have been able to correlate the data of this position to the position of the moving transceivers. So after analysis of the data that have been collected on the field, we get 6 runs, and actually it worked well with a surprisingly low deviation. So that was a very good experiment. We did also a Martian greenhouse, so astrobiology. We installed an inflatable growth chamber to accommodate 2 square meter microgreen hydroponic cultivation. The aim was the evaluation of the plant growth and performances in this kind of environment, and it was done for the Italian Space Agency. The results showed that the low night temperature, actually we had 10 degrees instead of the 16 that were expected, have a little bit affected the initial germination. So the germination and the growth of the seedling were delayed a little bit, causing at day 5 non-possibility to perform a complete panel of measurement. But then it improved, and at the end of the mission, we were able to see them at the performance that was expected, and we had also the opportunity to try them, and they were very tasty. We have also done some maintenance activities, so daily maintenance activities. On the left, you can see us doing some maintenance of the network and antennas. Was rather often due to the continuous wind that was turning the antenna slightly, but the rotation was enough to degrade or lose the... Okay, just one, so that's okay. The signal of the base station. On the right, we can see at the end of the day, so we're switching off the Wi-Fi network and change the batteries, and the day after you come back and you switch them up. Just one last slide on additional lessons learned that can be useful for the next mission. Environmental conditions have, even if they really well known, have a significant impact on the daily schedule. So we talk about temperature. So it had led to switch the start of the EVA from the beginning to the end. We changed the timing due to that. So it's something that can be important to take care of. The sound, we talked a little bit about that, the impact on the mechanics, and also the equipment, so they need to be very protected against that. Emergency procedure, just to finish with this, it's really important to really appropriate ourselves the emergency procedures during the mission, so we tried and repeat continuously in an environment that was representative of the real condition. So we trained for medical intervention, including the transportation means, the communication between the whole teams, Earth, Mars, but also the local security during this training on the emergency procedure. And it was continued training for during the whole year before the mission. And so we really thought on the field that it was very beneficial. Thank you for your attention. Do you have any questions?
I have to ask, how do you handle a fire in a spacesuit?
The fire on the spacesuit, so actually the batteries are at the back, and so the emergency procedure said that the analog astronaut has to bend over his knees, and so the safety officer has to just take the batteries, which are on the back. I can show you here. You can see the batteries are over there. Yeah. And so actually there's just a scratch that has been done around the batteries, and you can just take them off very quickly when he's bending in a way that he cannot move. And so you can stop the fire from that, and then you can help him.
Lithium-ion?
Sorry?
Are they lithium-ion? Are they lithium-ion batteries?
Yes, this is a lithium-ion battery, yes. So that's why we need to take care of that. Mm-hmm.
Question, how long did it take to design the spacesuits and build them, and what was your budget? And then the second question is, what's in the little silver dome up on top? Is it an LED display?
Here?
Yes.
So exactly, this is a LED display. So they can see the information, the main information on the screen. So they woke up and they see information that are important for them, like the timing and the next procedure that they have to execute. The spacesuit simulator itself has been developed over years. First missions with this were 10 years ago, and it's a continuous improvement. Actually, the EVS, yes, they have the patent for the spacesuit, so it means that they can improve, and really the simulations are done in order to improve the combination and the layers, the exoskeleton which is underneath, and with the resistance, and in order to feel like on Mars. So they're really, these experiments are really done in order to get a proof suit for Mars environments.
How much for each suit, like how much does each current evolution cost?
I won't be able to give you this kind of information today, but I can get the information if you want. Mm-hmm. There's two people. The ladies first.
Thanks, Bill. My question is, do you break sim at the end of the day, or do you actually stay in sim throughout the whole mission? The second question is, how long is your mission? Because you're saying that the seeds germinated, but is your mission longer than 2 weeks?
Yes, it was 4 weeks, and without breaking the seam at the end of the day. So it was.
Stay in sim throughout the whole mission.
Yes, so there was actually 5 weeks. The first one was Bridget phase, and the 4 next ones were simulation.
Did you have any analog instruments or detection devices to look for signs of life? In the soil experiments, you had some subsurface and some water detection instruments.
Yes, and actually we don't have the outcome of it for now. They have plenty of data they want to collect and analyze and see if they get further information than the previous ANAG mission that they did. So for now, I'm still waiting for the outcomes.
Oh, really? So they're culturing, I guess, the soil.
Mm-hmm. Yes, exactly.
Do you have many incidents that imply that in a Mars environment the suit would experience a puncture, or that the visor would experience a leak? I've always pictured in a sim the possibility that somebody like falls on their face and then, you know, kind of picks themselves up and says, oh, that crack isn't really cracked, and then goes back in the sim.
Right.
Yeah, actually, that was not something that we experiment.
Yeah.
Actually, the exoskeleton is really done for that. So it's a heavy spacesuit, but we put the weight at the rear part. So normally you have to fall on your ass. But then the thing is that when you need to bend in order to put something on the ground or take your samples, there's the exoskeleton that gives you this resistance and help you to support your suit and backpack without having difficulty to do it. So it's training, but it's not dangerous. So you don't need a table in order to do some things on the field. You really stay with your laptop and your box on the chest that it's openable, and there's a mirror so you can see also things that you are doing without having the need to look at it, really.
Were the suits custom tailored for each individual?
There's until maybe there's 2 spacesuits for now, plus 2 that are only used inside the operational center in order to debug. And there's a new spacesuit which is under elaboration, so the next generation. Yeah? Thank you very much.